Good morning everyone. Today I'll be presenting our project title Energy Driven Precision Scheduler EDPS, a reinforcement learning based energy optimization framework developed as a part of our hardware architecture deep learning course. Our team, myself and Uddhav, Danish, Rajesh, Yashwant, and implemented this framework entirely from the scratch at NIT Calicut. In simple terms, EDPS is a reinforcement learning system that learns how to assign different numerical precisions like 8 bits, 16 bits, or 32 bits to different layers of neural networks in order to save energy while keeping the accuracy drop minimal. The motivation and the aim of the project is deep neural network or computational expensive on hardware accelerators like GPUs, TPUs consume lot of energy during inference. We observe that not all layers need a high precision. Some can run safely with 8-bit computation saving energy while others require 32 bits of an accuracy. So our goal was to build an intelligent scheduler that automatically decides the best precision for each layer. Instead of hard coding rules, we use reinforcement learning to let the model learn these precision decisions through trial and error. So we model precision scheduling as a Markov decision process in which we have the three components to be discussed: a state, a 5-dimensional vector representing the layer, index number of maximum weights, activations, and the current energy usage. Second is the action, the precision choice, 8-bit, 16-bit, 32-bit. The third one depends on both energy and accuracy. If energy exceeds a given budget, we penalize the agent, otherwise we reward it for low accuracy drop and low energy by the end of an episode. After processing all the layers, the RL agent receives a final reward based on how energy efficient and accurate its configuration was. So let's discuss about the algorithm we used. It is reinforcement. We implemented a reinforcement policy gradient algorithm, one of the foundational RL methods. How it works. So here we go. The policy network predicts probability for choosing each precision. The agent samples say an action for the current layer. The action is nothing but the precision. Once all the layers was processed, we compute the reward. Then we update the policy in favor to the action that lead to high reward, that is energy efficient precision assignment. For simplicity, we start without entropy regularization or return normalization to make the baseline stable and interpretable. Future versions can include these important improvements for better learning. Consistency, let's discuss about the implementation. So we constructed our project into 6 modules, all implemented in Python using PyTorch and NumPy. So the first is energy model, which is a synthetic energy model that calculates the energy per layer based on the MAC, that is multiplication accumulation operations, and the bit width defines how 8-bit, 16-bit, 32-bit precision affects each energy consumption and accurate loss. So how accuracy loss model by sensitivity. So this served our virtual hardware energy simulator. And now let's discuss about the RL environment. So this environment is nothing but a gym environment in RL. So it manages the state transition, which layers we are on, what precision we choose, and what the resulting energy and accuracy penalty are. Each episode run through all the layers at the end returns the total energy and accuracy drop. So policy network, say in a small neural network have a 64 multi-layer perception outputs the probability of selection precision level. Then comes the policy gradient agent. This file is actually includes our reinforcement algorithm. It samples of action, collects trajectories, compute discounted returns, are updated. Updates the policy with entropy regularization. We trained the agent on 2000 episodes with a learning rate of 3 into 10 power minus 3 and a discount factor of 99.99. And let's come to the environment training script. The script connects the environment and the agent manages the critically evaluates the learn policy. So every 200 episodes it prints the total energy and the accuracy drop. Then the last model, that's the visualization model, which gives a Custom visualization is a graphical structure showing how precise choices affect cumulative energy. So let's go to the practical demonstration and that results. Let me share my screen. As my screen is visible, let me show you the code base. So as you can see, this is our code base where we have taken something like this. So we have the environment here which has a ED base file. This is an environment as we have discussed earlier. I have given a theory on idea like what script is doing what, and here we can see an episode starting state things like that. So reward is like here. So you can see there is a reward function like this. So we are giving an reward like minus 10 minus e total minus self dot e budget divided by e budget, something like accuracy penalty minus energy constraints. Then we have also taken care of the accuracy drop, as you can see in this else part. What next comes to the training script. So this is the training script, and as you can see here we have the 2000 episodes, the budget 6. This is policy PTS. This is a policy which we will adopting, that is stored as a parcel there. So let's go into it. We have a PG agent, and that's what we talked about something and this is visualization tree. So this is something, and policy net which we which we started with. As you can see, it is a model of like 64 is there. So it's a sequential layer. So as you can see, it's as simple as that. It's now let me do one thing. Sorry, let me run the program. So as you can see, I'm running the experiment training program. So that training basically hit this one, and you can see the files prints things after every 200. So you can see the 200 episode, 400, 600, 800 till 2000, and the final policy has been saved. So far you can see the episode 200 we have the energy total of 1.1 and the accuracy drop of 3. Then you can come to 400 where we got 1.17 and a drop of 0. So it may be not 0, but we have limited to the 4 decimal points, that's why. So as you go down, you can see we are trying. As you go down, you can see we are trying. The model starts with random selections. Okay, later it have learns that which exact path will be best optimizer path, and it schedules that you can see minimum accuracy drop will be there. So let's come back to my screen. So this is a demonstration which we have performed as an experiment. This can be further enhanced and seen that we have seen that learn to balance energy and accuracy. And let me show one more thing. So we have plot visualization as well. So let me show that second story here. As you can see, this is all for the nodes. So how complex it is. So there are too many nodes. So let me simplify it. So this can see the see the more is this color, that is more is energy use. The darker it is, the more energy it is. So the compact energy tree, as you can see, there are the 3 depth of 3, and you can start with have a very high energy requirement, whereas where you go up come down to a very least energy requirement, that is the lightest color. You can see that's the interpretability part of it. It's like a tree. You can have the multiple paths, and they have finally decided to come out this one RL path. So let's come back just a second. Yep, this was the demonstration that we are key insights and agents successfully learning adaptive precision scheduling across layers. So even without advanced techniques, we have seen a convergence, like training convergence smoothly, and visualization confirmed that the lowest energy configuration used mostly was a 8-bit and the darkest was 32-bit. So the entire pipeline was developed fully by us. It's not driven somewhere. What can be feature works? We can add normalization, entropy regulation. We can extend the actor, critic, or PPO methods for better than profile energy using real hardware instead of synthetic model. That can be done. So to conclude, I say that EDS framework demonstrate how reinforcement layering Horizontally learning can bridge the gap between the deep learning and hardware energy optimization. It's not only reduce energy but usage, but also provides interpretability insights into what our precision trade-offs occur in analytics. So thank you for your attention. This project taught us how RL can directly influence hardware level decisions and how small architecture choices can yield a large energy savings without sacrificing performance. Thank you very much.